Right, how's everybody doing? Super good, everybody's nice and quiet. Does mean everybody had a cruddy day like I did too? Alright, good. Or not good, but. Alright, so remind me real quick what we talked about last week, aside from breaking stuff. What's that?
Materials.
Material, yes, that's what we're going to continue to talk about today. So, last week we ended up talking about bonds and structures, if you guys recall, right? We talked about the different types of bonds, which you guys are all super familiar with, so we won't rehash that. But material structure is exceedingly important to how a material behaves. So tonight is going to get a little abstract. So we only have about an hour and change of content tonight, but I want to make sure that, so my point is we only have about an hour and change of content. But we have the whole 2 hours, so I want to make sure that if you guys have questions as we go, that you stop and ask, right? Because basically I want you to start preparing your mind to think in 3 dimensions, because obviously materials are in 3 dimensions. And we're going to start playing with ping pong balls tonight, right? So our ping pong balls are going to represent our atoms. So real quick, does anybody have any questions about, does anybody who have not done chemistry, or even those who have done chemistry, have any questions about structure of an atom, how that works fundamentally? No questions? Okay, everybody understands that there's a core, it's surrounded by electrons. Okay, good. So, if I have 2 atoms that are next to each other, what do they want to do? As if there's 2 of the same atom next to each other, what do they generally want to do?
Repel.
What's that? They want to repel. Why is that?
Because they're just in each other.
Yeah, so we have electrons in the outer shells, right? So they're going to push each other apart, right? And even if they're bonding, right, let's say that these 2 are covalently bound to each other, how close to each other can they get? They can't occupy the same space, right? And why is that?
Because of the electron they could.
Okay, well, there's actually still physically space occupied by that, right? So let's say that the edge of the ping pong balls is the outer shell of electrons, right? They're zooming around, right? These guys are electrons, are zooming around the core. So they can touch and they can share. Let's say they're covalently bound, so they're sharing right on the outer shell. But can they go on? They can't cross inner shells, and why is that? Why is that?
They knock some of the electrons out.
Well, they'd have to occupy the same space. Yes, they'd either have to do that or occupy the same space, and they can't do that, right? So fundamentally, remember our atoms can't occupy the same space. They can't be on top of each other, right? So even though we're thinking infinitesimally, that's why tonight we're going to be using ping pong balls, is because it's the best way to kind of represent that. Remember, our ping pong balls can move, they can slide on each other, okay? And we're going to stop mid-class. You're all going to get some ping pong balls to play with, and hopefully we can reduce the number of ping pong balls that hit the floor. But every year we always have some, so that's okay. Right, so tonight we're talking about the atomic structure of materials. And we start with what I was kind of already talking about, which is what we call the atomic hard sphere model. Okay? So for ease of visualization, imagine your ping pong balls. The closest that these atoms can get to each other is 2r, where r is the radius of the atom. Does that make sense? Right? And the radius of the atom is determined by what? Does anybody remember? The nucleus. What else?
Electron shells.
Yeah, the number of electron shells, right? So if we look at our periodic table, there's one in the back and there's one in the front, right? Radius generally gets larger as we go in what direction? So if I start at hydrogen, H, number 1 up in the upper left corner, radius gets larger as we go in which direction?
Right down.
Right and down. I heard it, right and down. Why is it right and down?
So when you go right, you add electrons.
Correct. When you go right, you add electrons, and when you go down, what are we doing?
You add shells.
We're adding shells, right? So they get bigger and bigger and bigger. Make sense? All right. So under this model, we consider our atoms to be rigid and impenetrable, meaning they can't touch. Yes, sir?
What exactly does this formula help with? I didn't catch that.
So there is no formula. It's just the idea, well, this will develop into a formula, but the idea is they can't be any closer than 2r. Yes, sir?
Wait, doesn't the radius to the right because there's more like protons, and then
When it goes up, I think it gets.
because it has more protons, and then that the outer
Oh, actually, I
shell-
think you're right.
Yeah.
No, yeah, you're right. It gets smaller as it goes to the right.
Yeah.
You're correct. You're correct.
Yeah.
Yeah, you're correct. Because it pulls it in.
Yeah.
Yeah, you're correct. All right. So again, let's just be very clear because that's exactly where JRM was going, I think, with this, right? Is the shortest distance between two atoms that can possibly be is the radius, right? Makes sense. They can't actually occupy the same space, so they must, the shortest they can do is touch on the edge. That doesn't mean they can't be out here pushing each other away, but the closest they can be is touching right here. Make sense? All right. Good. So, can somebody, before we go to the next slide, somebody remind me what crystallinity is? We kind of talked about it a bit last week. What is it?
Isn't it an organized structure?
Correct. It's maybe, right? So something that is a something that has high crystallinity is an organized structure. You're exactly correct. Right? Something that is all over the place or disordered. What do we call that? Does anybody remember? Amorphous. Very good, sir. Very good. And remind me of like an amorphous material.
Rock.
Glass. Right. Glass. All right. So just remember. But now I want you guys to think about what we talked last week in terms of crystal structure, but let's start thinking about in terms of atomic packing again with our ping pong balls. Okay? So what we have here is we have an amorphous structure with our ping pong balls. That's where our ping pong balls aren't necessarily fitting together very well. Right? You've got some of them next to each other, but there's no real finite way, there's no real ordered way that ping pong balls are sticking together. We then have monocrystalline, which is where the material or our ping pong ball structure is one big ordered structure, right? It goes on for infinity, it maintains the same order. And then we have last, over there on the right, what we call polycrystalline, and this is actually how the majority of crystalline materials exist, is where they have a chunk of crystal and a chunk of crystal and a chunk of crystal, but they're all kind of in one big material, right? Yes, sir?
Are there any monocrystalline substances then?
Yes, absolutely. So you can, a great example, and you guys may have actually done this in a science class before. Has anybody grown crystals before? Right? What do? You superheat the water, you put salt in, you oversaturate it, and then you cool it, and what happens to the salt is it gets cold. It starts to come out of solution, and it'll start to grow on your string, or you can put pin in there, or anything like that, right? The speed at which you do that will change. The speed at which you cool will change how long they have to go together. So you could build a single crystal salt crystal if you wanted to. The silicon wafers that we use in semiconductor manufacturing are single crystal. They do it they melt a whole pot of silicon, of sand, right? And they put a seed crystal in, and they very slowly pull it out, and as it cools, it forms a single crystal, and they get this whole big ingot, and then they cut the ingot up into the wafers. And it has to be single crystalline because the electrical properties are different, because if it's amorphous, if it's sand, it's different electrical properties. So excellent question. So amorphous, again, is something like glass. Monocrystalline would be like the example I just gave. There are other, so jet turbines, right? GE, who makes turbines, they put a lot of work into making sure that their turbines are as monocrystalline as possible, and they have as few defects as possible, right? Because to take a stab at it, right? If a polycrystalline material was to break, where do you think it would break? At the lines, right? At the boundaries between the crystals, right? So that monocrystalline, right? The ideal monocrystalline structure is super strong, and why is it super strong? Okay, if I want to actually snap that material in half, what do I have to do? I have to break the bonds, right? So in the monocrystalline case, I have to physically break the chemical bonds that are holding that together. Those could be ionic, those could be covalent, whatever, right? But I have to actually physically break that. Whereas in the polycrystalline, what I'm doing is I'm breaking the interactions between the two crystal planes, right? Very different. Yes?
So like lead, it's like ordered in layers. Would that be like the polycrystalline structure?
You mean graphite, right?
Yeah, graphite.
Yeah, so pencil graphite is technically polycrystalline, yes. Yes, it would be polycrystalline only because the layers aren't always, like if for some reason you could find it such that the layers were ordered perfectly, then I think you could make the argument that it was mono, but they never are, right? And that's, again, that's why you guys can shear it off and write with your pencils, is because it comes apart. Right. Excellent question. Any others? Okay, good, good questions. All right, so metals, alloys, and many ceramics are the type of stuff that we see in like polycrystalline, right? All right, so crystalline patterns matter because they go in all three directions, right? So it's, of course, very difficult for me to draw on here in 3 dimensions and have it make any sense, right? I've actually tried doing it and it just looks bad, right? So we look at them in two dimensions, but we need to remember that things go in all directions. So if we want to, if I was in the mood or I wanted to show you guys and represent a 3-dimensional structure, how do you guys think I would do that? Easily, without making it confusing. You have any ideas? What do you think?
Say that, by that you mean like show how something is 3-dimensional?
Mm-hmm.
Say that something has 3 measurements, the width, length, and...
Like an XYZ? Yeah, and you're correct. You do an XYZ. So let me cut to it. So because in a single crystal, or because our crystalline planes are considered to extend in all directions infinitely, right? Because it's the same repetitively, what we do is instead of showing the entire structure, we break it down to the smallest repeating unit, right? It's no different than like when we're doing polymers or something like that, right? Where we just talk about the one repeating unit. All we're going to do is we're just going to show the one block, knowing that that block continues ad infinitum, right? So what we're going to do is we're going to show what we call a unit cell. And it looks like this. So in this case, this unit cell would be this guy, right? But he would have 4 behind him as well. And this would be if these if these atoms were arranged just like this, forever and forever and forever, right? What we're showing is this one unit cell. So the simplest unit cell, now there are a lot of them, there's 13 of them actually, but the simplest unit cell to consider is one where all the atoms are at the corner of a cube, just like we showed there. Okay, and this is called the simple cubic. The volume of this unit cell, thus, and this is I think where JRAM was going, right? The volume of the cell is calculated by the same method. So now let's think about it, right? If I have these guys here that are making my unit cell, or my square in this case, what would be the volume of that square? Remind me, what's the radius of the atom?
2R.
R.
R.
So so what would the side of the square be?
4R.
The side would be what? 2R.
But it's
The face would be 4R. Because it's R,
from the
R.
center.
Okay.
so it's
Count it from the center.
2R. 2R. So what's the face? 2R times 2R is how much?
Or
So then what's the volume of the unit cell?
8.
8R cubed. Right? Right. Does that make sense? Does it make sense?
So-
For the ball, isn't the radius just half of it? So there are 2 balls, so.
No, the radius is from the center to the edge. You're thinking diameter.
Yeah, so that's why you have to multiply it by 4 for 2 balls, right? Because,
The
So
ring would be like the diameter length instead.
Right, so we have- So from here to here's R. From here to here's R. So that's 2R.
Oh, are you not like counting the outside, just like the, kind of like the inner part of it?
Yes. So yes, because yes. So look up there, and yeah, I think that's where we're failing, right? So if you look up there, the edge of that cube is at the center of the atom. And why does it have to be at the center of the atom? Okay, so remember this unit cell is representing something that keeps replicating over and over and over again. So it's at the center because this atom is also shared with what other unit cell? The unit cell right next to it, and the unit cell above it, and the unit cell in front of it, and the unit cell and the other unit cell in front of it, right? Right, so does that make sense now? So yeah, so your cell is 2R, 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 8R cubed, okay? Alright, so now let's think about this. So in the case of the unit cell itself is made up of how many atoms? 8. Kind of. Because those atoms are also shared, like we talked about, with unit cells next to it. So let's think about this. A unit cell that's in the corner, how many cubes is that shared with? Is it 4?
6.
Or is it 8?
7 other things.
7 other, yes, that's correct. It's shared with 7 other cubes. Right? Let's draw it. Let's draw it. Yeah, I guess you gotta kind of let your head think 3-dimensionally, right? It can be kind of tricky. So here, if we've got a cube, and now we have a cube. Now we have a cube. This guy right here, he's shared with 1, 2, 3, 4, but also the next 4 that are off the plane, right? So how many, again, is a corner piece shared with? 8. So how much of an atom does it contribute to that one cell? 1/8. All right, now let me ask you a question. How about one that is on the face of the square? So if it was on the face of the square, how many cells is it shared with?
1/4. Wait, well, the face.
The face of the square.
So it only has them to the top and sides.
Correct. So if I'm sitting here, how many other cells am I shared with?
4 cells.
1.
Oh wait.
Because we can only have 2 squares touching each other on the face. Right? How about if I'm on the edge now?
Oh boy. 4.
4 is the correct answer. Right. Very good. And how about if I'm in the middle of the cube?
9.
It's shared with how many? None is the correct answer. What's it? If it's in the middle, like if it's in the dead center of the cube, it's shared with none because it's all belonging to that one. If it's on the face of the cube, it's shared with one other, so 2, so that's a contribution of how much? 1 divided by 2, 1/2. If I'm on the edge and I'm shared with 4, that's a contribution of how much? 1/4, and if I'm on the corner, that's a contribution of how many? 1/8. Yes, sir.
What's the difference between on the face and the center?
So again, we need to think 3-dimensionally, right? So in this case,
Okay. So you're talking not necessarily in the corners.
so a guy here, so if we were to put a guy here, and let's drop him to here, into here, so he's in the center of the cube,
Okay, so the literal center.
literally the center of the cube, right? This guy, on the other hand, he's on the face.
So he's on like in the middle of those 4 points, but not in the middle of everything else.
Right. So if you were to do, let's do it from your XYZ. Okay, let's say your cube has an x of 1, so let's make it easier. X of 2, y of 2, z of 2. Its coordinates would be what? 1, 1, 1 to be in the center. Right? Whereas something on a face would be 1, 1, 0. Or 0, 1, 1, or whatever.
And is a
Right.
edge piece also a face piece then?
An edge piece
Yeah.
would have coordinates of what? 1, 0, 0, 0, 1, 1, whatever. And again, that's what makes it shared with 4. Make sense? Alright, so, yes, that's what we're talking about here. So a corner atom, 8 of them times 1/8, how many atoms are actually part of the simple cubic unit cell?
8.
Oh well.
1.
1. That's
yeah.
okay.
1.
Okay.
Got it? Alright, so this one is not in your book. It is just a sample problem. White 10, also known as beta 10, forms a crystal structure with the unit cell known as the body-centered tetragonal, as shown below. How many atoms are in this unit cell? So let's talk through it together. So
That would be 2.
we already know, just because of our last one, these guys are worth how much?
20.
1/8. And what's the guy worth in the center?
Nine.
Let's try it again. Let's try it again. What's the guy in the center worth?
1.
1!
Yeah, it's not shared with them.
He's not shared with anything, so he's worth 1, right? So this guy's shared with 8, this guy's shared with 8, you're correct there. This guy's shared with 0, correct there. But because he's shared with 0, he's worth 1 whole atom. The guys on the edge are shared with 8, so they're all worth how much?
1/8.
So how many total atoms are in this unit cell?
2.
2 is correct. Yes, 2 is correct. Oh, you guys are doing good. You guys are doing good. Alright, so again, corner atoms are worth 1. Center atoms worth 1. Corner atoms are worth 8, and there's 8 of them, so we have a total of 1 plus 1 equals 2. 2 atoms in there.
That's the hardest math problem.
Alright.
I think that's the hardest.
It's actually super easy, you just have to visualize it, right? Alright, so now what we're going to do is I'm going to pass out these little guys. I only have 7 of them, so you have to kind of share with people. So Alright, does everybody have all their ping pong balls ready to go?
You
Ish?
might be able to fit one there, but I doubt it.
Alright, perfect. Looks like we're good to go. Again, if you need another one, you can always hop up and grab one. It's not going to hurt my feelings if you get out of your chair. Alright, so let's do a quick reminder. So metals, we all know what metals are, right? They're shiny, they conduct well, they're malleable, and they're ductile, right? Somebody remind me, what's ductility?
Is it turn into a wire?
What's that?
The ability to be turned into.
That's exactly correct. Ductility is the ability to be pulled into a wire, right? So it's essentially its ability to be shaped without breaking, right? So we know that wires are ductile. We can kind of, metal wires are kind of ductile. We can kind of bend them, right? Now we talked about metals. Metals are characterized by what type of bonding? Metallic bonding, right? So this is going to best represent metals, because a majority of the metals, by this I mean our ping pong balls, are really going to best represent metals and metallic bonding. And why does it best represent metals and metallic bonding? Because it's non-directional, remember, right? Because our metals are kind of floating in. Remember last week I was talking about it's kind of it's the hippie commune, right? Everybody's just they kind of throw everything to the cloud. Everyone parties in the middle. They all think they have what they have, even though nobody has enough, right? All right, perfect. So the metallic bonding, of course, represents the structure material. So let me ask you guys a quick question. If I were to take those 2 boxes of ping pong balls and I were to dump them into a bucket, what would happen? How would they order themselves? Randomly?
Well, they have
We
some
try to
sort
organize
of
themselves, but there's no space.
Yeah, they'd fill the bottom and then they start going up. And they would try to kind of, just like you said, they would try to kind of form a structure, right? Like you might get a perfect coating on the bottom, and then maybe they start fitting into the holes of each other, right? But eventually one's going to not go right, you're going to get kind of a missing hole, and then you're going to get kind of a missed plane, right? And that's exactly what we were showing earlier with our polycrystalline material, right? Why do our ping pong balls want to go into that ordered state?
Because they have a confined area.
What's that?
They have a confined area.
They have a confined area. Why is that important? You're correct. Why is that important?
Because they're going to they're going to try and, I guess, do you have a finite number of these atoms?
Well, yeah, but any number of atoms are going to want to take up, like in your case, what you said, the smallest space possible. In this case, that's true, right? It may not be the case if there are 2 atoms that want to repel each other, like they want to take up more, right? But in this case, things always want to go to the lowest energy configuration, right? The closer in these things can get, I mean, it makes sense, right? Let's think about it from a metallic standpoint. Our electrons are floating around in the cloud, right? If the electron has to fly to the back of the room and back to keep 2 people happy, that's a lot of energy being wasted. If they can stick close and all the energy can stay around, It's lower energy configuration. Same reason that your covalent bonds they suck to each other, and they're not, covalent bond lengths aren't 20 miles, right? They're defined bond length based on this different atoms involved, right? But it's going to stay short, okay? So they want to go to the lowest energy configuration, okay? So what this results in is what we call close packing. Okay, because in metallic bonding, everything's in the cloud, there's nothing preventing the atom cores from touching each other, and by that I mean on the edge, right? Remember, they can't occupy the same space. Okay, there's nothing that prevents them from touching. They want to suck to each other as possible. Okay, because metallic bonding is non-directional, there's no restrictions on the number and positions of adjacent atoms. In order to form the strongest possible metallic bond, the individual atom cores will pack together as tightly as possible, and they'll try to do it as efficiently as possible. What we call this is close packing, and this arrangement allows for a minimization of volume, just like you were saying. It goes for high density, and it also maximizes the number of adjacent atoms, which we call nearest neighbors. Okay? Again, the terminology is not important, but fundamentally I want you to understand that if we pour it into the bucket, they're going to try to occupy the spaces in between because they want to be as close as possible. And in the case of our ping pong balls, what are they trying to reduce? They're trying to reduce the energy, the potential energy. They're trying to get as close as they can. Gravity is sucking them down, right, is what's happening. But in a realistic molecule or in a realistic atomic structure, they're trying to reduce essentially the pull on the electrons, right? They're trying to get as close to each other and be as efficient as possible. Okay, it's just nature. So now let me ask you this question. What is the largest number of atoms that can be close to each other in a perfect state? You can probably answer that question by looking at your ping pong balls, because what you guys were all trying to do was jam as many ping pong balls as you could into your little box, right? So, if I were to look at one atom, one ping pong ball, how many ping pong balls can I fit around that in all directions? 8? Is it 8?
If they're touching.
If they're all touching each other.
It's probably just 8 because.
Alright, that's fine. Let's think through it, right? So, no, that's okay. Let's think through it. So on a single plane, the most that can be packed around any single center sphere is 6. Right? You form your hexagons. Right? Okay, so now that we understand that there's 6, and looking at that structure up there, how many can I fit on the plane above it?
6. No. 7.
3?
Oh, wait, no. 1, 2, 3, 4.
If they're all touching.
No, yeah, direct. They have to be directly touching the center atom.
Oh.
The answer is 3.
3, yeah. 3. I was right.
And how many can I fit on the plane below?
3.
3 again? Are you sure?
Yeah.
Yes, the answer is 3. Yes, very good. Right. So now, how many can I fit around any single atom? 6, 3, and 3 equals what? 12. All right, good.
Myself for a second.
All right. So again, and you guys can try it, right, with your stacking. I promise you, you're not going to be able to get more than, without breaking my ping pong balls, please. You cannot get more than 12 ping pong balls around the center atom, or the center ping pong ball. All right. So the term closest packing refers to the most space-efficient configuration, which is, like we just talked about, what would we expect that to be? 12 is close packing. And the crystal structures of metals are thus defined by that, right? They're trying to minimize their potential energy. They're going to pack as close as possible. We're going to get 12 atoms next to each other. Okay? Now that's a maximum, right? Now what happens if I start changing the charges on some of my atoms? Do you think it's still 12? No, and why is that? Because things have to push away from each other, right? They can't just minimize their energy from gravity because they have to be away from each other, right? If we were to do the same thing with some strong magnets, what you'd find is it would not fall in the same way, right? Okay? So what we find is that we start getting, for lack of a better term, in 3 dimensions, we start forming sheets. Now I want to be careful using that term because we already kind of talked about that in graphite, right? Graphite actually is a distinct sheet. These guys are all part of the same crystal, but what we start forming is 2-dimensional sheets. Does that make sense? Layer upon layer upon layer. Okay? All right, so both structures formed by sheets both structures are formed by sheets of spheres, but they differ in how those sheets pack on top of one another. Okay, so there's two actual packing structures in the close arrangement that can happen. So let's walk through this together. And here's why I want you guys to kind of use your things and help visualize, okay? So we already talked about, in a single layer, the close packed hexagonal shape, there are gaps or holes between the atoms, right? You guys can see that in your boxes, right? There's a hole here where we can see through to infinity, the plane below, whatever you want to call it, right? We call these trigonal holes, and that's not very inventive. That's because there's how many points on that hole? 3, right? Makes perfect sense, okay? So, this is our flat plane now. And remember, how many closest neighbor, nearest neighbor atoms do I have in this plane? 6, right? Now, we know I can put 3 more in touch with that atom. So how do we want to do that? Well, we're going to place them in holes, right? Yeah, we're going to place them in holes to keep them nice and close, okay? So the second layer of atoms is then stacked on top of the first layer, such that atoms fall into the trigonal holes. Okay? Now, I want you guys right now to take your ping pong balls. You guys should have plenty, you guys should have a bottom layer and you should have a top layer. So now what I want you to do is just go ahead and look at that. Are all of the holes filled right now?
Well, this is on the side, so I'm gonna say. Wait.
Well, yeah, I mean, I don't mean the sides, obviously.
Right. Yes.
All of the holes are filled?
Well, they're not filled with their.
But can I put another atom? Can I put another ping pong ball in each of the holes up here? No?
Not in the hole, but like.
Well, not in the hole, but
top of
can
it.
I have one sitting inside the divot, whatever you want to call it, right? Yeah. Right? I can get a ping pong ball and everything here. I can fit one here, 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 right? You guys get the idea. Okay? So, no issue there. So now we're building our three-dimensional structure by adding layers. Okay? The first layer, no problem. Okay? We're adding those guys in right there. See, they go in those holes. They fit no problem. But now, we want to keep building our three-dimensional structure. So I need to add another layer. But now there's two ways that we can do this. Okay? We've created what we see are two different types of holes. You see this hole, you can see all the way through the structure. But this hole you can't. This hole has an atom right below it. So what we can do is one of two things, or what nature will do is one of two things. It will either place here, and then by extension here, and here, and here, and here, or it will place directly on top of the bottom layer. So what we either get is we get a repeating pattern, AB, 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 or we get a tri-repeating pattern, which is ABC, ABC, ABC. Oh yeah, I'm sorry. So we call this a tetrahedral, the one with it on top is called a tetrahedral hole, which makes sense because it forms a diamond. And the guy that's wide open is called an octahedral hole. It kind of looks like a weird star from the inside. Okay? Okay, so this is what I'd like you guys to do first with your little box, is build what we call the HCP structure, or the hexagonal close packed. And that is placement of the third layer such that you cover exactly the layer below.
Of a third layer?
Yeah, the third layer on top will cover exactly the layer below. So you got to make sure your guys are, in your little boxes, you got to make sure that your bottom layer is tightly packed.
No, I think we can just leave it as it is, and then just get more.
Yeah, you guys are fine. So it should be a 4, 3, 4 is all you're going to be able to fit in the box.
Yeah.
No. What? It's supposed to repeat itself, right?
Yeah.
That's not a repetition.
We do this.
That's not a repetition. What do you mean? You can't accept
You
yourself.
gotta be.
That's exactly what you did.
There's
Yeah, this is exactly what you did.
There's some slop there, it looks like. Yeah.
And then
Then we have one extra.
Yeah, you guys got it. Nice. You actually got 4 layers. Nice done.
Damn it.
Two more?
Need more bowls.
Right, so the HCP structure, hexagonal close packed, is going to look like this if we were to cut it in half. What it's going to do is it's going to look like this. It's going to be that AB, AB, AB structure.
Would you really? No.
Okay, now, I want, what's that?
One ping pong ball, whatever.
Oh, it got loose? Alright. Now I want you guys to build the alternate, which is where we do this. So now, look at the orange guys.
That's what we know.
So that's what you guys built? Yeah. So if we cover, in this case, the open holes, instead of the one below, we now get this weird kind of spiral. And actually, I think that's what you guys actually built. That's how you got 4 of them, right? Was that what you guys built?
Yeah.
Yeah. So the first one we did, the atoms on the second layer were directly above the first layer.
Yeah, they would put it back together.
In this one, you're going to have a 3-level stagger.
Oh, so it goes on the one
Probably.
off the keyboard.
Correct. It goes on the empty hole.
Okay, well there's only
I'm broken about
3 levels.
And ultimately, guys, what you should see is something like this.
I think we're just really
How did that even work?
Let's work.
Yeah, that's,
So we got a 4, 3, 4.
yeah, exactly. Yeah, that's the
No.
drive.
Wait a second.
It's the new one.
So,
Yeah.
oh, it's like down in there. Oh, it's there, right?
How did you do that?
How did this even work? It's not very good.
Yeah.
I think it's only 3 levels.
So now, there you go. That's the
Not 4.
stagger one. Or you can go like this.
On top?
We get rid of 3 of
Repeat.
a lot of these. Get rid of those 3 and then we put it outside. Or at least get rid of these. Then I think we can put it outside.
Alright, everybody have that built?
Nope.
Nope? Alright, well, tough. Alright, sit down. So, because what I want to do is I want to show you the cubic cells so that you can look at it in your structure before ping pong balls go flying. Alright, Jay, are you about done? Alright, so we looked at, so remind me, HCP is ABAB. Not remind me, I'm going to remind you. HCP is ABAB, and the FCC is ABC. Okay? So even though, do we all agree that these material structures have the same density? No, yes?
Yeah.
The answer is yes. It's still layers of closest packs. It's just how those layers are stacked. So these guys have exactly the same density. But if we calculate how the unit cells actually work, so remind me now, and this is where you have to start getting into it because this is now a hexagon. So how many unit cells is a corner shared within a hexagon? Yeah, it's still 12, right?
Yeah.
But how many was it in cube?
8.
8. Yeah, so it's 12. So it contributes 1. Wait, hold on. No, it's 6. Yeah, it's 6. I'm sorry, it's 6. It's 6.
Because egg was bigger.
Yeah, no, it is because they stack directly on top, right? So this one's shared with 1. So if we were to draw the hexagon, this guy is cut into basically thirds, right? And then third above, so 6. Yeah, sorry. All right. So this hexagon guy has 3 atoms that are completely inside. So those each give a value of how much? For a total of 3. No, they each give 1 for a total of 3. And then the guys on the edge, how many of them do I have?
Corners are on the face.
12?
Oh, corners?
I have 12 corner atoms because there's 6 on the top, there's 6 on the bottom, and they each give a 6, which is how many? 2. And then I have this face atom on the top, who's shared with how many?
2.
He shared across 2. He shared with 1. So he split 2. So there's 2 of those guys that have for 1. So now the unit cell here has a total of 6 atoms in it. However, the face-centered one, back to our cube, only has 4 in it. And you can do that math real quick. Again, this is a cube, which is super easy. We have 8 corners for how many? 1 total. We have 1, 2, 3, 4, 5, 6 faces at a half for a total of 3. There's none in the center, and that adds up to 4. So, real quick, different number of atoms, but same density. Which unit cell has to be larger? The one on the left, right? The hexagonal one has to be larger because it has more atoms of the same density. Okay? So now everybody should still have their FCC built, right? That's the one we built last, where it was going on top of the open holes. So now I want you to look at it. Can you actually see the unit cell within your ping pong balls? And I'll give you a hint. You have to turn your head like this. Alright, and then now, guys, your third layer, I want you to shift your third layer back to being directly on top. And see, this one's a lot easier to see because it is flat. See if you can find your hexagon. But think about it, right? And this is a good point. So our unit cell, right? All our unit cell is it's a repeating unit within the structure. So technically, if we wanted to, we could have it be 3, 6, 3. Right? Because that still repeats. It's just way easier to visualize if you put the 6 on the top. Yeah, but in this case, with the FCC, which is what they have the FCC, they're still trying to visualize it, right? It's not flat on your plane. It's into your plane. What's that?
What does that mean by saying it's into your plane?
Meaning it's kind of cocked within your plane, but it's still a repeating unit within your plane or within your material.
See the hexagon in there.
Yeah, the first one, the HCP, is very easy to see because it's flat against your desk, but the FCC is not. It's angled to your desk.
Oh, I see it.
You see it? There we go. See, once you see it, you can't unsee it. But
That's the bottom, right? 1, 2, 3, 4, 5. And
Nope,
then
I don't see
that'd
it.
be 1, 2. No, wait, the bottom is.
the bottom has 5. But remember, one's cut in half.
You can see there's 6 here,
Through here.
so it continues down there.
And then if you,
1, 2, 3, 4, 5.
that one underneath this one. And then
This is the.
The other one you need the other.
All right, so let's look at one more.
The cube one you need the
You
other.
guys, you guys found yours? All right, good.
Wait, what?
The FCC one.
This is
All right, so let's take our seats. Let's look at one more. So this one is the body-centered cubic, or the BCC. And I love it, right? She's like, whoa, mind blown. She finally saw it. I love it. All right. So, in the BCC structure, it's simply a cube, but now we have a guy living directly in the middle. This is not a close-packed structure. Why?
because
The
they
outside
can't
can't touch each
Space
other.
enough for the.
Correct. Right? The guys in the middle aren't touching on all 6 sides. He's not touching 6 different atoms, is he? Yeah, he's only touching how many? 4. Correct. Right? So now we have 1 center atom. We have 8 corner atoms for a total of 2 atoms in our unit cell. Okay? So this type of, so the structure we saw before is formed in perfect metallic bonding. This type of structure is typically formed in ionic bonding or mixed bonding, right? Where there's some sort of electrostatic forces that are pushing things away, or there are directional bonds forming them in that direction. Right, so in this case, it can't pack closely because there's either something pushing it away, or it's physically constrained by the angle of the bond between it and the other atoms. Make sense? Right, the reason we get the close packing out of metallic bonding because it's non-directional and they can float around, right? Just like a hippie commune, everybody's kind of moving around wherever they want, okay? All right, so there are 13 unit cells, and you have to memorize all of them before the end of class, okay? All right, point is, the shape of the unit cell, there are many of them, depend on the specific crystal structure. Oh, I said there are 13, I lied, there are 14. Sorry, there are 14 different unit cells based on 7 different crystal systems. But you can mostly see that there's a family, you can see them by family, right? There's this family of cubic ones, there's a family of rhombic ones, and then there's that Lone Ranger over there on his own, who's a weird tetrahedral diamond thing, right? Alright. So, now let's talk about ceramics, right? Somebody remind me what ceramics are again? What was the example I used last week? Breaking plates, right? Breaking plates, smashing a piggy bank, something like that. That's ceramic type materials, right? Glass is also a ceramic, okay? So, ceramics are typically compounds. Usually oxides, nitrides, carbides, something like that, right? And that means that it's not because it's not a single atom system, do you expect ceramics to be close-packed structures? The answer is no. We would start seeing something more like the body-centered, where it starts to form wider, less dense structures, right? And that kind of makes sense if you think about it inherently, right? Your metals, they're not, again, the metallic bonding does not keep them bound. That's why they can move around. That's why they can well fit. But they also tend to be pretty dense. They tend to be pretty heavy per unit area, right? Your ceramics, your piggy banks, your plates, they can be heavy, but they're not always. They can be a lot less dense, right? Because, think about it, we're packing literally less atoms into a larger space. Now, what's really cool about some of these is once we start getting to the point where we start combining atoms that are very different sizes, we can actually get to the point where we can fit smaller atoms inside of the various holes. And that's what starts to make things very strong. Okay? But ceramics encompass a vast array of materials, both crystalline and amorphous. They're relatively stiff and strong and very hard. But what happens when we drop a ceramic? Well, does it break? Yes, breaks is the correct answer. How does it break? Right? You guys are materials engineers now. It's the next step. How does it break? Shatters, right? Yes, sir.
Okay, so you just said the other atoms fitting in with other things. So that's the case, like an example would be like carbonized steel?
You can also do that in alloys.
Alloys?
Yes.
Okay.
Yes, absolutely. And why are alloys generally, well, what's one of the reasons alloys are generally better than normal pure metals?
Other than this?
A lot of them are stronger,
Oh, okay, yeah.
right? Yeah, so we'll talk about it in a second, but he's on it, right? So does anybody know what stainless steel is? Is stainless steel steel? What's steel? Where's steel on the periodic table? It's right down there somewhere.
I know, right?
What's the large? Does anybody know what the largest component in steel is? Iron. What else is in there? Carbon. What else is in there? There's some, and it actually depends on the alloy, but there's vanadium in there. There's nickel in there. You can find all sorts of stuff in there, right? Sometimes when we're troubleshooting stuff at work, we'll take what we call an EDX, which is an electrospectrum, right? You hit it and you bounce off. You hit it with a high pulse of energy, and it bounces off electrons at certain energies, and you capture that, and it can help you determine what actually is in it, right? Well, sometimes we'll get something. Usually we see silicon and carbon for obvious reasons. But sometimes we'll find weird metals, like where the heck did vanadium come from or something like that, right? And the answer is some steel part somewhere is shedding and somehow got into our chemical or something like that, right? So, and that's an important clarification actually leading into that. Ceramics do contain metal elements, right? Actually the elements themselves, but that doesn't necessarily mean that they're metals, okay? They're considered to be non-metallic because they do not display metallic bonding. Make sense? Another thing that makes ceramics very interesting from a materials perspective is that they primarily contain ionic, covalent, or a combination of them, right? It's not metallic bonding like we talked about. These strong bonds give rise to many of the properties, such as the high temperatures that we see and the strengths, but it also leads to what happens when we drop them. They shatter. Why? Because we broke those bonds and that's it, right? There's no bending. They're very strong. It's either broken or it's not, and that's why it will shatter. Okay? The structures are thus determined by the relative sizes of the different parts in there, the anions and the cations. Somebody remind me, what's an anion? Negative charge. What's a cation? Or a cation, right? You can say it either way. Cation, whatever. All right. So, here's the trick. Whereas before, when we were talking about our close packing, we always assumed that if some guy could fit 6 around him, he fit 6 around him. Okay? When we're talking about ceramics, that's not always the case. Just because somebody could have 6 friends doesn't mean he does have 6 friends. Okay? So a common one is the rock salt structure, which I'm showing here. Okay, this is a completely ionic compound with equal number of cations and anions, such as NaCl, right? Salt, sodium chloride, your old buddy, right? Other ionic compounds that form, you can't live without salt, whether you like it on your french fries or not, you can't live without it, alright? So other ionic compounds that form are potassium chloride, magnesium oxide, and iron oxide, right? Why would iron oxide be important, what we were just talking about? Steel, right? Alright, so what we end up forming is something like this, right? We get this alternating structure. Why does it have to be an alternating structure? Because they're ions and they have charges, right? What's the charge on, in this case, what's the charge on sodium? Well, there's not a charge on the overall, there's not a charge on NaCl. What's the charge on Na on its own? Positive. Na plus. Cl minus. Right? And then they trade, they become buddies, they stick together forever, BFFs forever. Okay? But would it make sense in our structure to have 2 anions close to each other? Heck no. Why? Because they want to push away from each other. What do the cations want to do from each other? They want to push away from each other, right? So they have to form this structure. So what we end up forming is, again, the rock salt structure, which is perfectly alternating. Now I do want to point out that, again, this is a unit cell. So technically, if you wanted, we could start our cube, if you want to call it that, with the cation in the bottom, and then have a cation layer on top, right? However you want to draw it. The idea is that it just repeats forever. Okay? So this one's relatively simple. This next one, I'll grant you, this one took me like multiple hours to draw, so don't say that you can't understand it. Just go with it, no. But point is, this guy is called the zinc blende structure. And this happens when there's an equal number of cations and anions, and all have 4 nearest neighbors. Okay? This is actually named, obviously, after zinc, because that's what it does. It's actually called zinc blende or spirolite. Any geologists in the house? No? All right. I probably killed that. But it's a form of zinc sulfide. All right. Point is, what we have here is we have 5 guys. So these guys are on the corners, and this guy's on the face. And then on the next, we have 1 on the faces, and then corner and face. But in between, the cations are there, but they alternate back and forth. So they're like this. And they have to fit their why? Because the charges, right? They have to go there. They can't go anywhere else because of the charges, okay? All right, who's heard of fluorite? So this is the fluorite structure. You can see these are starting to get way more complicated, right? Okay? So one such structure known as fluorite happens with much more complicated stoichiometry, and thus a much more complicated structure. So what happens here is now we have an anion that has what charge on it? 1 minus, but a cation that has what charge on it? Alright, so now in my whole structure, what does my total charge have to be? Has to be 0, and yes, that means they have to be equal, but it has to be 0. So, how many more cations do I have than anions? Half. Very good. I'll say it's a trick question. right? The answer is you have twice as many anions as cations, right? Because plus 2. So you have to have, so if it's a charge of plus 2, you have to have how many minus 2's to make it 0? Did I say that wrong? Yeah, how many 1 minuses? Sorry. You have to have 2 1 minuses to make it 0, right? So you have to have 2 anions for every cation you have. Okay, so you can see, right, now we have a different charge, and our structure has formed to be very different. So what do you think mechanically we can draw from this knowledge? But okay, let me ask a very simple question. If I wanted to slice this thing in half, or actually, if I wanted to break this thing, if I was pressing on this thing, where do we think this guy would break? Go show me. Where do you think this thing would break?
Oh, yeah, okay. In school. Okay. Okay. Sorry.
It happens every year. Every year.
Like along there because there isn't like a cation on the face.
So you think it's going to break vertically?
Yeah.
Okay. So realistically, it's probably going to break like this across the cell, because there's the least bonds to break there, right? But now we have to think about this another way, right? These are what type of bonds? Ionic, because they're charge-based bonds, right? So what happens? They're the same in all directions, or are they directional? They're same in all directions. Yeah. They're basically magnets in this case, right? Okay. So what you get is a very, very strong structure. Because look at that, right? That cation that's down here. This guy is holding in place how many other guys, for lack of a better term? Right. She's very popular at prom. She's got a lot of people around her. Okay. And here. But wait, what about this guy? What about these 4? There's nobody there. So this guy belongs to this back 8th quadrant, whatever you want to call it. This guy's in the front quadrant, this guy's in the back quadrant, this guy's in the front quadrant. So that means there's a cell here, and there's a cell here that doesn't have anything in it. So where are we going to break? More than likely it's going to pull apart in that location because it has less to keep it together. Right? Now we could solve that problem by doing what? Sticking something in those holes. What's the problem with that? Now we mess up our electrical properties. Or not electrical, our electrical stability. Okay? Alright. So this is the perovskite structure. And this is an ionic compound that contains more than one type of cation. So in this case we have the super small cation in the middle. We have the orange cations, which are around all the corners. And then we have the anions, which form the faces. Yes, sir?
What do you mean by different types of cations?
So in this case, it would be, so the perovskite structure happens in barium titanate, BaTiO3, right? So your O3 has a charge of what? Each O has a charge of what? Minus 2. Right? So the 3 O's produce a total charge of how much? Minus 6. What's the charge on barium? Plus 2. Let's consult our table. Does that make sense?
Yeah.
That's 2 plus 1. Yeah.
That makes sense.
And what's the charge on titanium? Yeah, usually it's 3.
We can't tell because none of this right here.
Oh, is it? Yes, exactly right. But right, where's barium on here? Somebody help me.
Yeah, I used to remember. 56. Oh, right there, 56.
56.
Minus.
So what's its charge?
Plus 2.
Plus 2. All right, ship it. So in this case, what's our titanium have to be?
Plus 1. Right?
I don't know what this is.
Wait. Minus. Wait.
I have.
Oh, now we're getting it. All right, let's try an easier one. Right? How about calcium? What's the charge on calcium?
1.
Oh wait, it's the same.
Ooh. Oh. Titanium. I
Right?
figured it out.
Calcium, titanium. Yeah, titanium's right here. He's in the no man's land of you never know what the heck it's going to be, right?
Oh, no, wait.
All right, let's move on to a simpler one. The corundum structure, right? We're back to our hexagons. But now in this case, those vacancies I drew, that means there's nothing there. Why is there nothing there in those vacancies?
Because it's have to do with like the electric thing.
Yeah, so let's think about this. What is the charge on O2? It's right there. Minus 2. Charge on aluminum is what? Plus 3. Okay. So that means we have electrical neutrality here with having 4, because remember all the oxygens are shared. Or not all of them, but not these guys. But these oxygens are shared. And why now do our vacancies mirror each other? Why couldn't I have why couldn't I have 2 vacancies right here and still maintain my electrical structure? It would work that way mathematically. But why are they going to form that opposite structure like that?
Because we have too many.
Why do you think, Madison?
You know, complement each other.
Very good. Yeah, I mean, they still are, but it's the lowest energy configuration, right? It's no different than this guy that we had a hard time visualizing, right? But this guy has 1 in the front, 1 in the back, 1 in the front, 1 in the back, right? They alternate, right? They're not going to sit on top of each other. They're going to get as spaced out and as even as they can and form the most repetitive, lowest energy structure that they can. All right. So everybody's sufficiently confused now? No, I mean, you shouldn't be, right? It's very fundamentally easy. It's just kind of hard to picture them when you're looking at the big things, right? Because it's not always easy to look at 3D, especially, you know, when some other engineer was trying to be an artist, right, and draw pictures, okay? So, all right. Silicates are the next important class of ceramic materials, and these are composed primarily of silicon and oxygen, but they're composed of silicon and oxygen in different ratios. You're going to about lose your toy, son. All right. So the basic structural unit in a silicate is silica, which is SiO2, which forms now we're talking about covalently bound structure. And what we form is this triangular tetrahedron shape that we see there, right? Silicon is the green guy in the middle, and he's surrounded by 4 silicon atoms. Now we kind of looked at that last week when we were talking about covalently bound carbon and how it forms that perfect structure with 107.5 degree bond angles, right? Because it has to, because these are covalently bound, and therefore they have to hold a certain structure because all the other guys try to push as far away as they can from each other. And when you're in three-dimensional space, they all become equidistant from each other, even if it's X, Y, Z, right? Still will work out. Okay? So this here I actually did SiO4 just to help emphasize the shape. But silicates are very interesting because they can form all sorts of different structures. We can get quartz, which we talked about last week. Remind me, what does quartz look like?
It's the white crystal.
It's a clear crystal.
Oh.
Right. Ideally. Right, if it's pure quartz, it'll be nice and clear. Right. We can make rings, or we can make sheets. And those sheets, just to be clear, those little lines coming off the sheets are to denote the triangles. There's not actually bonds between all of those, okay? The only bonds that exist are between the green and the largers, okay? We also get silicate glasses. Okay, so yes, sir?
For the triangle thing,
Mm-hmm.
why are those represented there?
Why are they represented there?
Yeah, why?
The easy answer is because it was hard as heck to actually draw that without, so what I did is I made a copy of the triangle,
it's
and I
an
copied
easy
and
way.
pasted and rotated it to make the rings.
Okay, so it's an easy way to draw that.
Yeah. Well, and because when you lay it out in a sheet, the reason I decided to leave them in instead of removing my guidelines was because when I looked at it, I couldn't make heads or tails of it, even though I knew exactly what I was looking at. It still looked confusing. So I figured it would be easier for you guys to visualize if you could look at it in terms of triangles instead of trying to follow each individual atom. Right? Whereas the problem with, if we go back, right, the problem with the silicate rings is if I were to leave the triangles in on the silicate rings, because I'm trying to show the ring end is two-dimensional, or sorry, it's three-dimensional, right? So see how I have the guys behind and in front of each other? If I were to draw the triangles in there, it was a little too much of an eye distraction. You see that, right? And quartz obviously is three-dimensional because I'm showing the full, well, it doesn't actually make a pyramid like that, but by showing the pyramid, I can try and show that it's three-dimensional. So these are my best non-professional artist ways of trying to show it. All right, so silicate glasses, a glass is any non-crystalline solid that is formed by cooling a material from the molten state, right? So we melt it, we pour it in water real fast, and what happens? It solidifies and forms glasses. Okay? Many silicate glasses are formed through the introduction of other cations, such as sodium, calcium, magnesium, etc., and by adding other oxides in the melt. And what these do, these are called modifiers. What they do is they actually screw up forming a crystalline network. They literally get in the way. So what we see here, the purple guy is a modifier, doesn't matter what it is, right? We see that our chains were trying to form, but instead our guy got in the way and they couldn't make it. Got in the way and couldn't make it. Okay? So this brings us to soda lime glass, which accounts for about 90% of the manufactured glass that you guys will see. It's inexpensive, it's probably what's in that window. It's made by melting soda, which is sodium carbonate, and lime together with silica at roughly 1700 degrees or so. And then they cool it. And the final structure is something close to what you see below. Right? So when you're looking through that glass window, it's not just melted sand. There's other stuff in there that's making sure that it doesn't crystallize. Because when it crystallizes, what can if it was a pure crystal, what would happen? You wouldn't be able to see through it. But quartz is a pure crystal, and you can see through that one. Why do we think? Okay, well let's ask some other questions, right? So there's lots of different types of glasses out there. Does anybody know what they intentionally do to car windshields?
They make it so that it will shatter.
They make it so it will shatter and not stick together, right? Why do we want that?
So you don't have a bunch of sharp objects.
What's that?
So you don't have a bunch of large, sharp.
So when you get hit, it doesn't explode in your face.
Yeah.
Right. And I think I said that backwards, right? They make it so that it will not shatter, right? So it'll kind of break and crack instead of going
Well, that's also partially because there's a plastic layer.
Yes, this is true, right? I mean, there's more design. There's more design to it than that, right? But you don't want two things, right? You don't want your car to get hit and have your whole windshield come and crush you, and you also don't want to have to explode and become shrapnel and be like a grenade going off in your face, right? Those would both be very bad things, right? So they design stuff accordingly. All right, who here is baked with Pyrex or something of the equivalent? Right? That is also a different type of glass that has been specially designed to be shatter resistant at higher temperatures. But has anybody ever seen like a cool YouTube video of Pyrex exploding? No? Maybe we should look one up after class. But if you heat it too quickly, or cool it too quickly, like if you take it and you throw it in cold water, what's going to happen to it? Right? The thermal shock. Okay? Alright. So that is actually all I have for materials. Alright, does anybody have any additional questions? Long class of lecture, but we had, plenty of ping pong balls flying around to keep us entertained. So. Alright, any questions? Okay, so next week I will be announcing this year's design competition. So we'll take the first 10 minutes of class or so to do that. And that's pretty much it. I will see you next week. Alright, thank you.